From Earth to space, there's no tougher 50 miles to cross. Fewer than 600 people have ever traveled it, but that number
Liftoff the Falcon 9 takes flight.
may be about to get a whole lot bigger.
Competition will drive the prices down, and we can enter a space age, a space 2.0.
Powered by entrepreneurs with bold new ideas.
Landing on a pillar of fire, that last 5 feet can be critical.
Elon Musk set himself up to do something that no one else says he can do. If he delivers, it might change the world.
And NASA daring to dream big once again.
We're working on the next heavy lift rocket that will take us farther than we've ever gone before.
It's giving the nation what it wants in a very exciting next generation space program.
Space. It's never been closer. For humans and machines. It's the rise of the rockets. Lifting off right now on Nova.
T-minus 1 minute, 35 seconds on the Apollo mission. The flight to land the first men on the moon.
Kennedy Space Center, Cape Canaveral, Florida. Launch Complex 39.
T-minus 17, final guidance release.
From here, every Saturn V Apollo mission and every space shuttle lifted off.
Liftoff. Liftoff on Apollo 11.
But after the final space shuttle landing in 2011, NASA tore down its Pad 39 launch gantries. And since then, no American astronaut has flown into orbit from U.S. soil.
The one hole in U.S. space capability right now is the ability to transport humans into orbit or beyond.
The U.S. has spent more than $100 billion building and operating the space station, and we can't even get there unless we pay and overpay the Russians to do it.
It's not where we want to be as a country. It's not where we want to be as an agency.
But now, Launch Complex 39 is back in business. Rebuilt with the goal of flying astronauts once more.
3, 2,
And this time, the rockets are not only NASA-owned and operated. Private company SpaceX is already launching its Falcon rockets, ferrying supplies to the International Space Station. Eventually, they hope to become a major provider of human flights to the station as well. And SpaceX isn't alone.
A number of private companies have stepped up and started providing economical, reusable, recyclable launch capabilities to deliver to space.
But what about NASA? They're focusing on pure exploration with a new rocket to take humans into deep space.
we're working on the next heavy lift rocket that will take us farther than we've ever gone before. It will be the most powerful rocket ever built.
At the same time, the audacious technical achievement of SpaceX's reusable rocket and their stunts, like launching a car and dummy driver out of Earth orbit, have ignited new public enthusiasm. If you believe the hype, then we're on the brink of a new era of spaceflight. But great uncertainties lie ahead. The demand for seats remains tiny, with only governments and a handful of private citizens willing to pay for an expensive ride to space. So will this lead to a renaissance in space travel, or fizzle out? Nothing more than a flash in the pan that fails to take the next giant leap for humankind.
Liftoff the Falcon 9 takes flight with the Dragon spacecraft destined for the one-of-a-kind laboratory in microgravity, the International Space Station.
we're in the midst of a revolution. A surge of commercial rocketry that could make space more accessible and usher in a new chapter of exploration.
And liftoff.
It's a revolution that was started by NASA. In 2005, the agency decided to commercialize the task of flying cargo and crew to the International Space Station, freeing NASA to take on bigger challenges.
It allows NASA to focus on bolder expeditions for deeper space exploration, putting human beings on Mars and other worlds, pushing beyond the envelope and giving the nation what it wants in a very exciting next-generation space program.
NASA's next-generation space program calls for a big new rocket capable of carrying humans beyond Earth orbit once again, to the Moon, or even Mars. It's a return to NASA's roots.
NASA is recreating a 21st century version of the Saturn V as an exploration vehicle. The heavy lift vehicle intended to enable the resumption of human exploration beyond low Earth orbit.
We're developing the Space Launch System to carry crew and heavy cargo first to the Moon or in near lunar orbit, and eventually to Mars and the outer planets.
Already 8 years in development, NASA's Space Launch System, or SLS as it's known, is designed to carry 50 tons of spacecraft and human cargo beyond Earth orbit.
It will be able to take the large systems that we need to land to an outpost to do the exploration in deep space and to deliver payload and humans necessary to do the research on the Moon.
If all goes well, in the early 2020s, NASA's new rocket will send a human-rated spacecraft around the Moon, the first since the days of Apollo. The second mission will follow a similar flight path with humans on board, the first such voyage in over 50 years.
Its initial target mission is to bring astronauts in orbit around the Moon in order to lay the groundwork for a new space station that will orbit the Moon and an eventual return to the Moon by US astronauts and robots.
The SLS is the latest in a long line of NASA's human-rated rockets, starting with the one that carried Alan Shepard on his famous 15-minute flight in 1961. These liquid-fueled rockets all share common features. Engines at their base, fed by powerful pumps that draw propellant from the tanks above. Perched above all this is the payload, the cargo to be delivered to space. As payloads got bigger, so did the rockets required to launch them, culminating in the Saturn V, capable of carrying over 48 tons to the Moon.
2 minutes, 30 seconds and counting. We're still go on Apollo 11 at this time.
And the Space Shuttle, built to routinely haul up to 32 tons to orbit.
1, 0, and liftoff, the final liftoff of Atlantis, shoulders of the Space Shuttle.
NASA's new rocket, the SLS, will be even larger than the Saturn V. But rather than designing from scratch, NASA has borrowed technologies that have flown before.
This SLS is a cross between the Apollo, which had the capsule at the top, and the shuttle, which had the 2 solid rocket boosters on each side. So if you look at Apollo and shuttle, you can see the similarities of both of them coming together to form SLS.
The SLS has not yet flown, but as these aspirational NASA animations suggest, it will be quite a sight at liftoff.
The minute the SLS launches off the pad, it will be the most powerful rocket ever made.
Building the most powerful rocket in history is full of challenges, not least the size of the rocket. Even a single fuel tank like this one is enormous. A building big enough to put this giant rocket together inside is so vast, the engineers use bicycles to get around. Even the tools they're working with to assemble the rocket are gigantic.
I'm your welding metals engineer here for NASA. This is the Vertical Assembly Center, and it's the largest weld tool in the world, and it's the only one of its kind.
The weld tool, a giant tower, tackles the tank in sections called barrels, welding them together vertically.
When we're assembling a tank, it's done in different stages. So one barrel is welded to the dome, and then once that's been welded and checked and verified, then another barrel is brought in. And so to assemble a hydrogen tank, and you have 5 of those barrels, and then the very last piece is the bottom, the aft dome.
The tanks are welded using friction to melt the metals together, generated by spinning the tool head at high speed. It looks easy, but in reality, the construction of this first hydrogen tank has been plagued by problems, putting the rocket far behind schedule.
It's a very troubled program, basically. The SLS will cost at least $8.9 billion through 2021, which is double the amount initially planned.
It's now 10 years later, a couple $1 billion a year. It's continuing to be delayed.
Overruns aside, it's an ambitious new rocket. But why does it have to be so big? Larger than any other? The answer lies in the fundamentals of rocket science. At its heart, rocket science is all about propulsion, and a principle that was first described by Isaac Newton, whose third law of motion states, for every action, there's an equal and opposite reaction.
So the principle behind a rocket is actually really simple. All we really have here is what's called a mass engine. If we have enough mass inside and we push it out fast enough, then what we're going to be able to do through Newton's law, action and reaction, is to propel this rocket, I hope, skywards.
First, mass. We're going to pour water into a tank inside our rocket to add mass.
And as we fill it up, I can feel the rocket actually getting heavier. That's a good sign, because that gives us more mass, more propulsion to get the rocket to go that much further.
Second, a source of energy to push the water out of the back of the rocket as fast as possible. For that, we're going to use high-pressure air from this compressor.
And so now all I need to do is to release the compressed air into the rocket itself. Pressurizing.
The compressed air raises the pressure in the rocket's water tank, which is prevented from escaping until
5, 4, 3, 2, 1, go! Yay!
When released, the high-pressure air pushes the mass of water out of the nozzle at high speed, producing thrust that propels the rocket in the opposite direction, skywards. That's why it's called a mass engine.
And so there we are, the principle of action and reaction. As we push the water out the bottom, the rocket goes up. And so the question is, how much fuel and how fast do you have to eject it in order to get a rocket into space?
This question is at the heart of all rocket science. The combination of the mass of propellant, in this case water, and the speed you're pushing it out the back is what propels you into the air. But you can't get to space using cold, relatively slow water. Propelling a rocket fast enough to reach space requires something much lighter, moving much faster, like rapidly expanding hot gas. The idea of using such a hot gas rocket to reach space was first published in 1903 by Russian mathematician and scientist Konstantin Tsiolkovsky. He worked out the best way of generating a lot of hot gas expanding very rapidly. Gunpowder, or black powder, seemed like a good way to do that. It's what humans used for centuries to fire everything from arrows to cannonballs and rifle bullets. And it's one of the main fuels in fireworks.
And I've got a small jar of it here. And what we'll do is we'll just quickly take a look at what happens when it lights. Here we go. Let's go. Oof. It's pretty fast.
When ignited, the gunpowder reacts with oxygen, releasing a lot of energy and turning it into a rapidly expanding hot gas. Seems like an ideal fuel for a rocket. But there's a problem with solid fuel like gunpowder. Once ignited, it burns until the reaction is over. But in a rocket, it's preferable to have a fuel that can be controlled.
Tsiolkovsky's crucial insight was the fact that if you light a solid fuel, then the burn kind of goes on until it runs out. If, on the other hand, he were to use liquid fuels, then he would be able to control how much liquid was being poured into the flame. In other words, he would be able to exert even greater control over his rocket.
Tsiolkovsky started casting around for the right liquid fuel to use. At the time, high-quality liquid fuels like kerosene and gasoline were becoming available thanks to the emerging petrochemical industry. Here on Earth, these fuels burn by reacting with oxygen in the atmosphere. But in space, there is no air. So Tsiolkovsky proposed carrying a supply of oxygen along with the fuel. It would take an American scientist, also obsessed with the idea of spaceflight, to build such a rocket. His name was Robert Goddard.
So what Robert Goddard came up with was the idea of combining liquid kerosene with liquid oxygen. And by burning the two together, he would get a fierce flame that he could control, and that would really push his rocket skyward.
When the kerosene reacts with the oxygen, the result is a very hot, rapidly expanding gas. And if channeled through a nozzle, that hot, fast-moving gas produces thrust that can push the rocket in the opposite direction.
What we get is an enormous expansion, an enormous push. But above all, we can control it.
With just such a design, on the 16th of March, 1926, Robert Goddard finally launched the very first liquid-fueled rocket in history. The flight was brief. The rocket didn't go far or fast, but the potential was clear. Carrying liquid oxygen on board meant rockets could fly beyond the Earth's atmosphere.
And with that, Robert Goddard imagined we could go to the moon.
Goddard might have dreamed of reaching the moon, but his liquid rockets never even reached 2 miles into the sky. And that's because of something called Tsiolkovsky's rocket equation.
When Tsiolkovsky was thinking about how to power a rocket, one of the things that he realized was that you're not just moving the payload, you've also got to move the fuel. And the fuel itself has weight. Now you can imagine putting more and more fuel in order to power your rocket more, but at the same time, you're adding more and more weight.
Tsiolkovsky tried to describe this catch-22 problem by considering things like the mass of the rocket, the fuel and the payload, and the velocity it would need to reach to get to orbit. The longer the engine burns, the more velocity the rocket will have. But longer burning means more fuel, making the rocket heavier and harder to push. It's a vicious cycle, and still bedevils rocket scientists today. To travel fast enough to deliver a payload into space, most of the rocket has to be fuel.
The critical consequence of the Tsiolkovsky equation is the fact that, really rather depressingly, only a tiny percentage of a rocket can ever be payload. And when you think back to the lunar missions of the Apollo space program, Those enormous rockets were used to fire just 3 men.
NASA's giant Saturn V, the largest, most powerful rocket ever to fly. Built in a hurry to race to the moon, engineers hacked the rocket equation by building the Saturn V in a series of disposable stages, where each set of tanks and engines were discarded as they ran dry, shedding weight and allowing the next rocket stage to accelerate even faster. But even a giant staging rocket the size of the Saturn V wouldn't be large enough to carry the Apollo spacecraft all the way to the moon without the right fuel. Kerosene wouldn't do. In fact, there's only one fuel that packs enough punch. A fuel that Tsiolkovsky himself had also proposed.
Tsiolkovsky's focus on the chemistry that's available to us and its crucial role in being able to push a rocket led him inescapably to the conclusion that he needed the lightest and yet most energetic fuel possible, and that had to be hydrogen.
The power of hydrogen compared to other fuels is easy to demonstrate using a homemade cannon and some sacrificial potatoes. First up, regular gasoline.
Really using the same sort of fuel that you might put in a car or in an airplane. Here we are. Now we'll screw the end over the barrel. Okay, right. So here we go. And now all it needs is that vital spark.
When ignited, the highly reactive gasoline vapors are converted into a very hot, fast expanding gas that pushes the potato out of the cannon.
Whoa!
Gasoline has carried the potato just over the bushes into the next field. Now the same experiment, but instead of gasoline, we'll try the same mass of hydrogen, an invisible gas.
And so I've got the hydrogen here in these monster syringes, which we've preloaded with a little bit of hydrogen in each one. We're gonna cap the whole thing up. And I'll tell you, this thing is a really pretty scary explosive mixture. This one is going to be really loud. Here we go. Ready, aim, fire! Whoa!
Hydrogen is the lightest element in the universe, so you can pack a lot more atoms into each pound of fuel. And when it reacts with oxygen, it burns with a near-invisible flame, producing a very familiar substance, water, which expands rapidly as a hot vapor.
Whoa! That was the biggest distance yet.
Whether you're launching potatoes across fields or big heavy payloads into deep space, there's no more efficient fuel to use. And that's why the Saturn V's upper stages also used hydrogen fuel to get it to the moon. The main engines of NASA's new SLS rocket will also be powered by hydrogen. It's an engine called the RS-25. This model powered all 135 space shuttles to orbit. It's an incredible record that makes the RS-25 one of the most reliable rocket engines in history, and NASA wants to repurpose them for the SLS. It's built by a company called Aerojet Rocketdyne. Tom Martin works at their world-class engine test facility here at NASA's Stennis Space Center in Mississippi.
The RS-25 was originally developed in the 1970s and 80s throughout the shuttle program.
5, 4, we've gone for main engine start. We have main engine start.
Some of these engines have been in multiple flights in space, very reliable, very high performing.
There were 3 of these RS-25 engines located at the tail of each shuttle. At launch, they were supported by 2 detachable solid-fueled boosters.
Its speed now 320 miles per hour.
But the 3 main engines were part of the shuttle itself and returned to Earth each time to be used again and again. But will they work on NASA's new rocket? Today, they're going to simulate a full SLS 8-minute launch to space on one of the engines to test the control of its flight computers.
You can see the A2 test stand, and then further off in the distance, the A1 test stand. The A1 is where the RS-25 is going to be tested here in just a couple of minutes.
Close to the test engine are 300,000 gallons of highly explosive liquefied hydrogen and oxygen.
A crew will go in right before test and verify that there aren't any leaks. Everything looks good.
And we are standing by for the RS-25 engine test.
Okay, it sounds like we're 2 minutes away. All right. Nothing's 100% guaranteed, so there's always a little bit of nerves before a test. We do everything we can to make sure the tests and the flights are going to go off, but there's always unknowns that creep up. We'll evacuate the area to at least a quarter mile, so if anything bad does happen, we want everybody to stay safe. Most of the test crew is in the test control center. That's where they control and monitor the engine.
Keeping a safe distance is crucial, because when an engine fails, the results can be often catastrophic, as seen in this early Apollo engine test.
So you can hear the siren. That means we're 1 minute away.
Sounds like auto sequence has started.
At this point, the computers take over. It's kind of under the computer command. The engine goes from 0 thrust to full thrust in about 5 seconds.
As the engine hits full power, the temperature reaches 6,000 degrees, accelerating the exhaust out at 13 times the speed of sound. Guzzling 1,500 gallons of propellant each second, it's now generating just over 500,000 pounds of thrust. The heavy steel structure of the test stand keeps it firmly grounded, while the exhaust is diverted out to the side using enormous flame buckets. These billowing clouds of combustion gas are just water vapor, formed as the hydrogen burns in oxygen. And like naturally formed clouds, sometimes they make rainbows.
You don't really get a sense for what these machines are doing until you're on the ground seeing a test, and then you get the full impact of how powerful this stuff is and how hard it is to get things into space. It never gets old seeing the test. I can see it every day.
535-second test of the RS-25 engine has concluded.
The engine's flight computer has performed flawlessly, controlling the throttling of the rocket through the simulated ascent to space.
It gives me goosebumps every time I hear the engine start. I mean, it's a visceral experience to see an engine test.
If it all goes as planned, the engine they've tested today will power the first SLS rocket in the early 2020s. And like the Saturn V, this engine, along with most of the rest of the rocket, will be dropped into the ocean never to be used again after just one flight. That's at least part of the reason why getting huge heavy payloads into deep space is still so expensive. But is that the only solution? Why not reuse your rocket like an airliner? That question poses an array of new challenges.
The airplane, if you threw it away after every flight, would be a very expensive way to travel. In the beginning of aviation, we created vehicles to be reused. For rocketry, we somehow forgot that, and we're not benefiting from reusability. We threw away everything when we were done.
And that's because making a landing from space by re-entering the atmosphere at a speed of 5 miles a second is much harder than landing a plane from a cruising speed of over 800 feet per second. After the Apollo mission, NASA tried to build a reusable space plane through the 1970s, the iconic Space Shuttle.
And the shuttle has cleared the tower.
But there were problems from the start.
The Space Shuttle was supposed to travel every other week. 40 times a year was their proposal, which would have dropped the cost significantly. We thought if you're reusing an engine, it's going to be less expensive. But they had to pretty much take apart and rebuild the shuttle main engines after every flight. The Space Shuttle never was able to launch regularly, and it was very, very expensive. About $1 billion a flight.
Footing that kind of bill was not sustainable for NASA. And in the early 1990s, the agency started funding research into other ways of making rockets reusable. Engineer John Garvey was on the team.
There are different ways to do reusability, and many advocates believe that a vertical lander is the way to go. If you can just come down on the same engines that you launch on.
They developed an experimental rocket known as the Delta Clipper. It was a radical departure, as this rarely seen footage shows.
Delta Clipper Experimental, or DCX, was an experimental vertical takeoff, vertical landing rocket.
Unlike the Space Shuttle, which was designed to fly back to Earth, the Delta Clipper would land on its tail.
Test flights of the DCX began in the early 1990s at a desert testing ground out in New Mexico. Nothing like this had ever been attempted before.
We took it out to White Sands missile range out in New Mexico and launched it multiple times.
This footage looks like outtakes from a science fiction movie.
It flew, maybe 10,000 feet, but it was demonstrating that it was possible to get the rocket back and fly it with minimum refurbishment, reduced cost.
The engineering team was on top of the world, but their fortunes were about to change.
There was a line that was not hooked up, and as a result, as it was landing, only 3 of the landing legs deployed. The 4th one did not. So it actually landed successfully, and I was like, yep, let's go.
Landing small negative. Engine out. She's coming over.
And then you turn around, and then the rocket's gone, it's on the side, and the tanks are rupturing. Yeah, it was a tough day, but that's how if you're in this business, you got to get used to it. You got to roll with it and just say that's part of the deal. And if you can't handle it, don't do it.
Losing the entire vehicle before it reached space led NASA to cancel the program to pursue other avenues. But there was one person who saw the potential, a South African-born entrepreneur who'd made his first fortune disrupting the banking industry with a company called PayPal, Elon Musk.
Musk had always been a science fiction fan and interested in the possibilities of colonizing other planets. And after he became wealthy as an entrepreneur, he had some money he could put toward this kind of scheme. And that's how SpaceX was born.
There have to be reasons that you get up in the morning and you want to live. Like, why do you want to live? What's the point? What inspires you? What do you love about the future? And if we're not out there, if the future does not include being out there among the stars, and being a multi-planet species, I find that it's incredibly depressing if that's not the future that we're going to have.
In the early 2000s, there was little business incentive in building rockets to take people to space, let alone Mars. But that was about to change.
GNC, you ready? Flight Max, we're ready. GNC's go.
And we're ready, Willie. No deltas.
On the 1st of February 2003, NASA's oldest space shuttle, Columbia, was returning from orbit.
Columbia, Houston, UHF, com check.
Loss of voice communication is always expected for a short time during re-entry. But on this occasion, contact was never reestablished with Columbia. Damage during launch, which no one had noticed, caused Columbia to burn up during re-entry over America, killing all on board.
GC plane. Flight GC, lock the doors. Copy.
The risks of flying such a complex spacecraft were brought into sharp focus. It was time for NASA to rethink how they launched their astronauts into space.
There was a decision after the Columbia accident in 2003 to retire the shuttle as soon as the International Space Station was fully assembled.
Rather than build a new spacecraft themselves to reach the space station, NASA decided they would buy future astronaut seats and cargo delivery missions from private companies. The man charged with finding and developing those suppliers was Alan Lindenmoyer.
SpaceX was a new startup company. They had only been in business for a few years, and when we visited them, they had maybe a couple hundred people. They were very busy, and we could sense and we could see that this was an extremely talented team that we believed had the ability to complete it, the job.
Closing a deal with NASA to send cargo and crew to the space station was a huge boost to SpaceX, but also a risk for the space agency. So they appointed their longtime aerospace partner Boeing to build another new crew vehicle to fly on their existing single-use rockets like the Atlas V. SpaceX was in the spotlight as they set about trying to develop a brand new reusable rocket.
It's classic Elon Musk. He's set himself up to do something that no one else says he can do or is really asking for, but if he delivers, it might change the world.
Attempting to fly a reusable rocket to space and back is about as hard as aerospace engineering gets.
It's hard enough building a rocket that can get to orbit. Now if you have to build the additional capability to bring it back, the margins get even tighter.
Returning a rocket safely back to the launch site involves a series of complex steps, which begin on the edge of space when still traveling at over 3,500 miles per hour.
First, the rocket does what's called a boost back burn. It fires its engines, slows itself down, and starts returning in the opposite direction.
Now on a trajectory that's taking it back towards the launch site, this giant 14-story tower must turn itself around once more to point the engines forward as it starts to re-enter the top of the atmosphere. And that's when things begin to get tricky.
A rocket is an unstable vehicle. You have to deal with the control elements, so how do you keep it stable on the way down?
It has maneuvering jets at the top that shoot out bursts of compressed air to keep it aligned, but its main way to keep going in the right direction are something called grid fins.
These fins, the size of dining tables, act as paddles to steer and slow the falling booster rocket as it enters the denser lower atmosphere.
As the rocket gets closer and closer to land, it does more controlled burns with its engine to slow down and align itself with the landing pad.
As the engine ignites into a hypersonic headwind, the 33-ton rocket suddenly becomes even more unstable.
It's like balancing a pencil on the end of your finger, and think of how much effort and work you need to do that yourself.
An array of sensors is now constantly relaying the rocket's orientation to the engine at the base that swings left and right to keep the vehicle upright as it slows down.
Landing on a pillar of fire, that last 5 feet can be critical. If you don't know where the ground is.
Approaching the landing pad, the onboard autopilot now deploys legs and throttles back the engine so that velocity and altitude both equal 0 together.
All of these different variables just show how much has to go right every time the rocket comes back to Earth for it to land.
Easy to pull off in a slick animation, but a long shot in real life. Then another internet entrepreneur with similar dreams stepped forward. Amazon founder Jeff Bezos, who'd quietly founded a company in the year 2000 called Blue Origin.
One example of the secrecy behind Blue Origin is the first time we really learned what they were doing is when a journalist went through their trash cans outside of their office in Washington and discovered the plans, or at least memos discussing their goals of space tourism.
Working quietly without fanfare, it takes Bezos and Musk more than a decade to pull off their first successful vertical landing rockets. Bezos' rocket, named New Shepard, after the first American astronaut Alan Shepard, reached the edge of space on the 23rd of November 2015 and returned to the launch pad a few minutes later. Within a month, Musk's first reusable SpaceX rocket booster, called the Falcon 9, touched down vertically too, after delivering a payload all the way to orbit. These two triumphs marked a major step in the pursuit of a more reusable rocket, and perhaps the beginning of a new era for lower-cost trips to Earth orbit, and the long-awaited promise of more affordable space tourism. While SpaceX has continued its successful track record, with over 20 commercial launches in 2018 alone, another quieter rocket revolution is underway, one that's being driven by miniaturization.
Today, everybody knows that microchips, batteries, solar panels are smaller and more powerful than they ever have been. But what that allows engineers to do is build small satellites that are cheaper and weigh much less, but can do everything old satellites do.
Such small, low-cost satellites, some known as CubeSats, can be deployed very quickly and may transform the way we communicate, navigate, and observe Earth from space.
One of the advantages of having multiple spacecrafts working in synergy with one another is that you can monitor things like wildfires that are spreading rapidly. You can do this in real time. We can track earthquakes, whether or not it's going to shoot off a tsunami. We have much more data to be able to pinpoint the location of catastrophic events and then take action to remedy that.
This new generation of tiny satellites is spawning a new array of rocket launch companies. Because thanks to Tsiolkovsky's rocket equation, once the payloads are smaller, the mass of fuel can be smaller too. And that makes it cheaper to get to orbit. One company aiming at this new market is Rocket Lab. Its founder is New Zealand engineer Peter Beck.
The whole purpose of Rocket Lab is to enable frequent, affordable access to space. And if we can do that, then some really incredible things will start to happen.
Until Rocket Lab came along, the most affordable rocket ride to orbit would set you back around $60 million. But they can do it for less than a tenth of this price.
Our prices start at $5.7 million. So that's a dramatic order of magnitude change.
5, 4, 3, 2.
Getting to orbit for this sort of price requires a new approach to rocket building.
It's the world's first all-carbon composite launch vehicle to ever reach orbit. The carbon fiber gives us a strong advantage with mass and structural performance.
Using carbon fiber instead of heavier metal alloys reduces the rocket's weight, allowing for more payload.
The rockets are incredibly light. You can wheel it around with no issues at all. The actual structures in the tanks of the rocket weigh almost nothing.
Rocket Lab has already put 24 CubeSats into orbit on 3 flights. They hope their radically cheaper carbon fiber rocket will create even greater demand for launch services. Hacking the rocket equation can bring costs down, but only so far. So innovators are looking at other ways to economize. For example, what if a rocket doesn't need to take off from a launch pad? eliminating the expensive infrastructure which accompanies all liftoffs. What if you could launch to orbit from almost anywhere, even from the back of a truck? That's exactly what Delta Clipper veteran John Garvey is trying to do.
We've designed the rocket certain ways to make it simpler. We use a trailer, drive it a mile or two to the pad, go vertical, and launch. We basically need a paved road, a concrete pad, and some utilities, power, and the internet's nice.
By focusing on really small satellites, under 130 pounds in weight, Garvey can reduce the size of his rocket, allowing him to experiment with much cheaper solutions.
We use liquid oxygen as the oxidizer, and we're using propylene as the fuel. It gives us just enough extra performance, the thrust on the order of 20,000 pounds at liftoff.
Garvey's rocket engines might be puny compared to NASA's main SLS engine, but they have the potential to change the way we launch very small satellites in a very big way.
Our job is to get to the point where when we launch, people don't even look up. It's just like, oh yeah, okay, fine. And we'll be truly successful, we collectively as an industry, when we're doing that and people barely look over and say, oh yeah, that's another Vector launch. They do that all the time. That's going to be the metric that we are really establishing. We're hitting the numbers.
Garvey imagines a low-cost mass market where rides to orbit are as mundane as jet travel. Another way to reduce cost to orbit is to start your rocket closer to space by eliminating the need to launch from the ground at all. One company, Virgin Orbit, thinks it can cut launch to orbit costs down by allowing the rocket to hitch a ride partway to space. Their CEO is Dan Hart.
Well, Virgin has been working on air launch systems for quite a while. And so there's a whole Virgin Galactic company that is working on space tourism, where a spaceship comes off of an aircraft and takes tourists into space. And from that, the discussion of, well, what else can we get into space? And how can we use similar technologies really rose.
Virgin Galactic's rockets are designed to carry a relatively heavy cargo of humans high enough to reach space, but not fast enough to get into orbit. But by reducing the mass of the payload, a small rocket carried to altitude under the wing of a plane could reach the speeds needed to get to orbit.
So it was an easy, logical progression to use those technologies for the purpose of taking satellites into space.
Spin-off Virgin Orbit has a fully reusable first-stage launch vehicle in the shape of a repurposed jumbo jet airliner, christened Cosmic Girl.
Cosmic Girl is the carrier aircraft. She'll carry our rocket Launcher 1 to about 35,000 feet and get close to Mach 1. Speed of sound, having altitude and velocity is a good thing for a rocket to start off with. And it gives us an initial boost. That helps us because it allows us to make the rocket smaller and less expensive.
Just like Vector and Rocket Lab, Virgin Orbit's also chasing the burgeoning small satellite market. So, are there enough new small satellite companies to keep all these new rocket companies in business?
The eternal bane of all rocket companies is making sure there's enough cargo for you to launch in the future. And with so many rocket companies forming right now, it's not clear that they'll all survive.
While these small rocket companies fight it out to see who will become king of the microsatellite market, the bigger players, like NASA, SpaceX, Boeing, and Blue Origin, grapple with the challenges of carrying immense payloads into deep space.
Elon Musk and Jeff Bezos are talking about millions of people living in space habitats or colonizing Mars. And even though it sounds crazy, it is a difference in their approach, and it shows in how they try and do things, to be cheap, to be long-lasting, to be infrastructure that can be built on by the broader economy, not just a one-time military mission.
Behind these ventures is a common impulse, one that drives some of us to build rockets.
We're all explorers. We're departing from low Earth orbit, and we're going to go further than we've ever gone before. And I think that we're really going to do this someday.
SpaceX has announced it is building prototypes of its giant Starship rocket, intended to ferry hundreds of people to Mars. So could today's rise of the rocket really carry us all to the stars?
I really believe that just like we are now taking humans to low Earth orbit commercially, that pretty soon there will be a commercial space station in orbit as well, which will be the next destination. So what I tell people is, if you don't think you can go to space today, just wait. 100 years ago, when all there were biplanes that didn't fly very fast, the average person would say, I will never fly an airplane. So you have to think about, what's it going to be like tomorrow?
100 years after the first powered flight, airplanes and air travel are commonplace, something we take for granted. Will the same be true of rockets 100 years after Goddard's first flight? Will this be the dawn of an age that ultimately propels society even further?